Before considering the octahedral and tetrahedral voids in a hexagonal closed packed crystal, let me revise some of the concepts we learnt with regard to the octahedral and tetrahedral voids in the cubic closed packed crystal. So we saw that there are two kinds of voids of importance. This is the octahedron and the regular tetrahedron. We also saw that, for instance, this is the position of the tetrahedral void within the common unit cell, which is starting from one corner. And we saw that within a unit cell there are 8 of such tetrahedra, and we saw that the octahedron is located at a body center and also at the edge centers, as the body center is related to the edge center by the phase centering translation, which is half 0. Now we also saw that suppose I have a 2 tetrahedral voids and an octahedral void in the middle, this combination can act like a primitive unit cell for the cubic closed packed crystal, and therefore this is the primitive unit cell. So it consists of 1 octahedra in the center and 2 tetrahedra, and they are joined along the body diagonal of the cube. Now let us try to look at an alternate model of this FCC voids, so that we can understand that how some of the tetrahedra and octahedra are packed within the unit cell. And the most important thing for that I am going to use this model which I have got here. The most important thing we noted was that the octahedral void is shared between 4 unit cells. That means within a unit cell you got only 1/4 of an octahedral void. So to illustrate that, I have got the model in front of me here, and here you can see these are my octahedral voids, and you can see that this is 1/4 of an octahedral void. So how do I understand it's 1/4? I can put together 4 of these voids which are located here in front of me to make a regular octahedron. So I put together 4 of these and I get a regular octahedron. So in the unit cell, I said there are 2 positions I would like to distinguish for an octahedral void. One is the body center, which I will take out these tetrahedral voids and show that actually the body center is the seat of an octahedral void here. So this is my octahedral void which is located at the body center. These 4 positions are tetrahedral voids which are starting from these vertices of the cube, these corners of the cube, and therefore I got 4 tetrahedral voids. These blue faces you see are nothing but the faces of the octahedral void which are sitting on these vertical edges. So this edge, as I said, all edge centers are centers of octahedral void positions. And similarly the bottom positions, like you can see the bottom vertices also have octahedral voids at their center, and this can equally be seen by the top edges here. So let me do the repacking to show you how these tetrahedral and octahedral voids fit together. So I already have in position 4 quarters of octahedral voids at the 4 edges of which make the bottom face. The 4 vertical edges, there are 4 quarters of an octahedral void already sitting in place. Then I place the 1 octahedral void in the body center. So this is my octahedral void which goes in the body center. The next thing I do is put these tetrahedral voids in place. So I got 4 of these tetrahedral voids here, and therefore I got total of 8 tetrahedral voids, 4 pink tetrahedral voids at the top, 4 pink at the bottom, which we already saw when I removed these pieces. And now these 4 quarters of octahedral voids which you can see here, there is the green faces are the faces which have been cut, and therefore when I join these green faces together I get my regular octahedron. So I cut this into 4 quarters and put 1 quarter each in one of the edges, and this octahedral void is shared between 4 unit cells. So particularly suppose I take this octahedral void, it is shared between this unit cell, the unit cell above it, the unit cell to the left of it, and the unit cell below that. So it's shared between 4 unit cells, and therefore the contribution of this octahedral void to this unit cell is just 1/4. So since I have 12 edges, 1/4 into 12, 3 plus 1 at the body center, therefore there are 4 octahedral voids per cell, which matches exactly with the number of atoms in the cubic closed packed structure, which is 4. Therefore for every atom in the cubic closed packed structure I have 1 octahedral void, and as I saw there are 8 tetrahedral voids, which implies for every atom in the cubic closed packed crystal I have 2 tetrahedral voids, and therefore I have 8 tetrahedral voids. So this void model is very illustrative in understanding that how voids themselves can be cut and associated with unit cells. So this is an important model, and you need to keep this picture in view in understanding that what is the contribution of voids to a single unit cell when you do a counting. So, we had seen that the tetrahedral void in the cubic closed packed crystal is a smaller void, but there are twice as many tetrahedral voids as octahedral voids, and if you look at the size ratio of the voids atom which can sit in the void with respect to the radius of the atom at the lattice point, it is 0.225 for the tetrahedral void and 0.414 for the octahedral void. Later on we will actually try to compare this, we will convert this radius ratio into actual dimensions for certain, like for instance the iron crystal, and then try to compare with the, for instance, the carbon atom which actually goes and tries to sit in some of these voids. So, in that case you will get a realistic feel of what these void sizes mean with respect to the atoms sitting in the lattice positions. So, therefore, this also tells you another important point, that I need to know not only the total volume available, but how it is partitioned between, that is the total volume available in the form of voids, but I also need how it is partitioned between the various kinds of voids and how numerous those voids are. Okay. Now, let me take up the voids in the hexagonal closed packed crystal, and we had already mentioned that the hexagonal closed packed crystal has identical voids as compared to the cubic closed packed crystal. In other words, it has got a regular octahedron and a regular tetrahedron as its voids. Now, what are the position of these voids in the unit cell? So, you can see here in this hexagonal closed packed crystal unit cell that the tetrahedral void is formed between 3 atoms in the basal plane and the atom which is located in the mid plane. So, the position of this void would be, for instance, this is actually in the centroid position, it is 1/4 way above. So, it is actually the void positions are written here as 1/3, 2/3, 1/4 and 1/3, 2/3, 3/4. This is for the octahedral void, and the coordinates for the tetrahedral void are written here. Now, it is so this tetrahedral void, for instance, will be located 2/3, 1/3, 1/8. So, this is the position of the tetrahedral void. Now, we will actually take up models to understand where these tetrahedral and octahedral voids are located, and in this case, in the case of the hexagonal closed packed crystal, it is actually very difficult to visualize, especially the octahedral void. Now, the packing direction, we are packing upwards, is the 0001 direction of the hexagonal closed packed crystal. In other words, the direction of the packing of the closed packed planes. So, we are packing the closed packed planes in AB fashion in the direction which is the C direction. Now, the difficulty in visualizing the octahedral void comes from the following, that actually if you look at the octahedral void, it is sitting not within a single unit cell, but within multiple unit cells. So, for instance, suppose when I want to visualize this octahedral void, it is sitting, say this is my unit cell, it is sitting between one unit cell, the second unit cell and the third unit cell. So, it is shared between 3 unit cells, and this makes visualization of this octahedral void more difficult. The tetrahedral void is easy to visualize. It's, for instance, this is one position of tetrahedral void, and there is an equivalent position of the tetrahedral void. But now, if you look at with respect to the orientation of the tetrahedron, this tetrahedron is oriented upwards. But if you look at the tetrahedron in this figure, it is oriented downwards. So, this tetrahedron is formed by the 3 atoms in the mid plane, and suppose I am talking about, say, zinc crystal, this would be 3 zinc atoms sitting in the mid plane and the atom which is shared between 3 unit cells. So, now therefore, this tetrahedron is shared between multiple unit cells, and more importantly, it is oriented the other way around as compared to the tetrahedron in this figure. As we will see that using models especially, that the octahedron has got a single orientation in the hexagonal closed packed crystal, while the tetrahedron has got 2 orientations. Okay. And to repeat, the voids are identical to those found in the cubic closed packed crystal. So, there is no difference between the voids, and this will become obvious when I show you the models which are used to illustrate the point. Now, let me try to understand where the octahedral void is in the hexagonal closed packed crystal and how we can pack these octahedral voids and along with the tetrahedral voids to fill space. This exercise we had undertaken for the cubic closed packed crystal, and this was an easy exercise because we could actually cut the octahedral voids into 1/4, take them, put them along the edges, and then include full tetrahedral voids along with one full octahedral void to fill an unit cell. Once the packing of a single unit cell has been achieved, then I know the packing of the crystal can be achieved. But as I pointed out, in the case of this octahedral void in hexagonal closed packed crystal, this truncation is not is not very illustrative. In fact, the truncation, if you were to do, will be down this plane, and therefore you will be cutting this octahedron along this plane, which goes down this direction, and it is difficult to visualize. So, for instance, this is my orientation of the octahedron with respect to 2 unit cells in the hexagonal closed pack crystal. This shows an alternate view of that, wherein I have included 3 atoms in the mid plane and 3 atoms in the basal plane. All the atoms as before are identical. They have been colored differently just for better visualization. So, looking down the 0, 0, 0, 1 direction, in other words the C direction, I see that this is the direction of my 3-fold in the cubic hexagonal closed pack crystal. You can see that these 3 atoms come from the C equal to half plane, and these 3 atoms come from the basal plane. So, now the way I start my packing is actually putting 3 octahedra together the way I have done here. So, these 3 octahedra are put together, and the space left in between is what is colored in orange, is an tetrahedron which is pointing upwards. Therefore, I can put my octahedra together and then put one tetrahedron in the middle of these 3 octahedron which is pointing upwards. Therefore, and further I can put other octahedra around this and go on to fill entire space. But now this is not filling of space with a single polyhedron, but with 2 platonic solids, the octahedron and the tetrahedron. These points will become clearer when you actually take up the real models, wooden models which I have got here, and as I told you, these are the seat of the void models, or this is the picture I use, which I call the void model picture. Now, I would also like to know how many voids are present per cell, and this calculation again can be performed either based on the diagrams I am showing here or based on the void models I am using. So, the number of voids per atom in FCC and HCP, we will see this, that actually I can go from, when I am making a layer by layer construction of void models, that I can go from an FCC to an HCP crystal by a 60-degree rotation around the central atom. So, this I will show you using the model, and the central atom which I am using has been marked here. So, as I just to revise, what are these void models? Void models are wherein atoms have been shrunk to points, and I use a polyhedral shape to denote the coordination around a central void atom sitting in the void. Okay. Now, let us look at the number of voids per cell and voids per atom in the tetrahedral and octahedral voids. In HCP, there are 4, you can see these are the positions of the tetrahedral void. There are 4 voids per cell, and the number of voids per atom is 2. In for octahedral voids, again there are 2 positions I have shown here. There are 2 voids per cell, and there is 1 void per atom. Ravi has a question.
Sir, I want to know the difference between voids per cell and voids per atom.
Okay. As you know, in FCC there are 4 atoms in the unit cell, right? Therefore, I may have, for instance, number of tetrahedral voids in an FCC or a cubic closed pack crystal is 8, but then you have 4 atoms in the unit cell. So, I divide them, that 8 by 4, and get 2. So, that is what I am doing here. Okay. In the case of the HCP, you got 2 atoms per cell. So, that is clear. So, I divide the factor by 2. Now, in order to better visualize the position of these voids, I have certain other diagrams here, and wherein the hexagonal unit cell has been split into various planes. So, this is plane, for instance, located at 0, this is a plane located at half, this is a plane located at 1/4, this is 3/4 and 1. Similarly, there is a diagram on the right hand side which has been used to locate the positions of the tetrahedral void. So, you can see that if you make such a diagram, then there are 2 octahedral void positions, and these are on the centroid of the triangles, and this is one in this plane, and there is one in this plane. Similarly, when you look at the tetrahedral void, you can see that in the basal plane there is one center of the tetrahedral void here. Then there is this is not the basal plane, this is the plane which is located 1/8 above. So, this is 1, 2, 3, 4, 5, 6, 7, 8. So, this is 1/8 above, and therefore, I have one tetrahedral void center sitting there. Similarly, in the plane which is this 1/8, 2/8, 3/8, I can see that there are centers of 4 tetrahedral voids. Then this is 4/8, 5/8, I can see again 4 tetrahedral voids, and as you know, this again would be repeated upwards in the plane which is above. So, now I can locate, and this diagram is useful because it actually helps you in localizing it with respect to the triangles, these triangular prisms. So, this is now my basal unit cell, and this is half triangle, and I can locate them with respect to the centroid of the hexagonal unit cell.
So, what is the difference between basal plane and single plane?
No, these are all basal plane. What I mean, these are all of course stacking of basal planes, but this is shifted up above. Okay, this is in the C direction. This is 1, 2, 3, 4. So this is C 1/4. Okay, so there are two octahedral voids, one at C equal to 1/4, and there is one at C equal to 3/4. That's what I am showing there in a diagram like this. So because as I pointed out, locating and associating these octahedral and tetrahedral voids in a hexagonal closed packed crystal is somewhat difficult, and visualizing them with respect to especially the unit cell. In the cubic closed packed crystal, there is a different kind of a problem, wherein you are packing along the 111 direction, typically the closed packed layers, but you typically visualize a unit cell of the cubic closed packed crystal along the 100 direction, which is a 4-fold direction. In other words, you do the packing of the closed packed layers along the 3-fold direction or the 6-fold direction of the individual planes, that is the 111 direction of the cube, but you visualize this unit cell typically along the 4-fold direction. While in the hexagonal closed packed crystal, you draw and visualize these planes along the original 6-fold of these individual layers, which later on becomes, as we saw, a 6-3 screw axis or a 3-fold. But even in this case, because of the strange orientation of the octahedron, typically when we draw an octahedron, we typically end up drawing an octahedron with the 4-fold upward. But in this case, I have to visualize an octahedron with a 3-fold upward. So let me show with respect to a model, for instance. Actually, it is related to the fact that the way we normally draw octahedra, we normally end up drawing octahedra this way. It would have been equally instructive for us to draw an octahedron like this. That means with a 3-fold upward, right? But we rarely draw octahedra like this, and therefore it becomes difficult for us to visualize how we can draw an octahedron like this and how this octahedron is shared between unit cells in the conventional representation of the hexagonal closed packed crystal. That is where the issue is, and that is why we require a certain amount of time to be spent in understanding these voids in the hexagonal closed packed crystal. So if once we start drawing octahedra like this and start visualizing along the 3-fold of this octahedron, then it becomes very easy for us to understand where the octahedron sits in the hexagonal closed packed crystal.
So, this is the octahedral voids in Q. So, how we can see this have only one rotation, one orientation, and tetrahedral have 2 orientation. So, we can see in crystals. How we can see the models?
Very good question, and I will show you that to you when I take up the wood models. So, I will just do that for you next. So the point I am trying to make here is that when we want to understand octahedral voids in hexagonal closed packed crystals, you need to have multiple ways of understanding the same. You need to look at them using pictures like this, wherein I am drawing plane by plane and locating the centroids of these voids. I am using actually these voids to do a space filling. So there are many ways I can locate the same octahedra and tetrahedra. And this is very, very important, because otherwise it is very difficult to localize these octahedra and understand how they actually fill space to form the hexagonal closed packed crystal. So let us try to understand the position of the octahedral and tetrahedral voids, which gives rise to the hexagonal closed packed crystal and also the cubic closed packed crystal. So here I have my regular octahedron and my regular tetrahedron, which have been placed along my direction of packing, which is now the 0001 packing in the hexagonal closed packed crystal and the 111 direction of the cubic closed packed crystal. Now any such, for instance, when you take a tetrahedron, actually represents 2 layers of atoms, because there is one atom which has been reduced to a point here and there are 3 atoms which are here. Similarly, this also represents 2 layers of atoms, because there are 1 layer of atoms at the bottom here and there is 1 more layer of atoms at the top. So any such figure actually represents 2 layers of atoms, wherein atoms have been shrunk to points as we do in a standard void model. So let me start with an tetrahedron and put 3 octahedrons around it, or octahedra around it. Now as you can see, the central tetrahedron is in a upward orientation, while all these 3 octahedra are in the same orientation. Now I could continue in the plane by putting more and more of these octahedra, which all will happen to be in the same orientation. Now I have got voids here between these octahedra, wherein I can put additional tetrahedra in the upward orientation like this. So far I have got all my tetrahedra in the upward orientation, and they sit here, 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 and one right at the center. So now further I can of course put tetrahedra right here also and propagate this order throughout my plane, this two dimensional plane, which actually, as you might note, is actually two planes of atoms, because there is one plane which is the plane of the paper, and there is an additional plane here where there are atoms. Now when I want to complete this layer, two layers of atoms, I will have to put additionally this tetrahedra in the second orientation, which is oriented downwards. So this is my second variation of the tetrahedron, and it is downwards. So I have constructed two layers of atoms which now can extend to infinity. To make another layer above this, I have two options. So I have an octahedron, for instance, and I can put, so I call, say, this position of the octahedron as the A position, then this would be a B position. Now suppose I put a tetrahedron, an octahedron on top of an octahedron, then I would see that this is my A position, this is my B position, but this position is exactly above the original position, which is A position. Therefore I will get an A, B, A. So I am putting octahedron, octahedron, therefore I will get an A, B kind of a packing. In other words, whenever I put an octahedron on an octahedron to make the second layer of voids, which would actually constitute three layers of atoms, then I would get an AB kind of packing, which would give me the hexagonal close packed crystal. Now instead of putting an octahedron on an octahedron, suppose I put a tetrahedron on an octahedron like this, then I will get an A, then a B, and this is a new position which was not there in the two layers of atoms below this, and therefore this would be a C position, and therefore whenever I put a tetrahedron on an octahedron, I would get an ABC kind of packing. In other words, I would get the cubic close packed crystal packing. So let me start off by putting and taking an octahedron, trying to make the third layer of atoms, and put an octahedron on top of an octahedron, existing octahedron. So this is my position, an octahedron on an octahedron. Similarly, I can take an octahedron, put it on this existing octahedron. You take another octahedron and put it on this existing octahedron. Now you can see that these octahedra are actually leave a hole in the center, which wherein a tetrahedron can fit, and they also leave holes here in these positions wherein additional tetrahedra can fit. Right. I can do that. Now an important point to be noted at this stage is that suppose I am looking at a central atom, an atom which is located here, then using these void models I can calculate the number of atoms which come together at this void. In other words, number of voids per atom, I can make a calculation very easily. So first, suppose the atom sitting here would be shared between 1, 2, 3 octahedra which are below this, and there are 1, 2, 3, 4 tetrahedra. When I make the next layer, as we were trying to do just now, then you will have 3 octahedra in the plane above, and there will be 4 tetrahedra. In other words, 3 plus 3, 6 octahedra come together at a single vertex in the hexagonal close packed crystal, and as we shall see, this number remains unaltered when you go from an hexagonal close packed crystal to an cubic close packed crystal. So 1, 2, 3 octahedra in this plane plus 3 above, 6 octahedra coming together at each atom, 1, 2, 3 in bottom orientation, 1 in the top orientation, 4 tetrahedra up here, 4 tetrahedra above. So 8 tetrahedra coming together at a vertex in, that means, which is an atom in the cubic close packed and the hexagonal close packed crystals. This could have equally well been visualized by an alternate models which we have considered before. For instance, we have a model like this here, and I have an atom here, and I can for instance take this atom, and I will use the camera above to actually show you that, for instance, there are 8, we have seen here 3, 1, 2, 3 tetrahedra, 4 here. So there will be 8 unit cells, and there are 8 tetrahedra coming together. As we saw, this is 1 tetrahedron here, 8 of them. Similarly, octahedra, there is 1 from here, 1 from which is shared between these unit cells. Similarly, you can see that we can visualize using alternate models, this calculate the number, that there are actually 6 tetrahedra or 6 octahedra coming together at a vertex. So let us return to the void models once again. Now let me make the second layer of atoms by putting an octahedron on, or a third layer of atom, the second layer of voids, to make an void model or a void space filling model. So I got my layer 1 of atoms here, the layer 2 of atoms here, the layer 3 of atoms above. So I got 3 layers of atoms and 2 layers of voids, and now this structure can be propagated throughout to actually get the hexagonal close packed crystal. And this is an hexagonal close packed crystal because we started off by putting an octahedron on top of an octahedron. So this is how we started off. Now let me do the other alternative, which will lead to the cubic close packed crystal, which is by putting an tetrahedron on top of an octahedron, or equivalently I can put an octahedron on top of this tetrahedron. So I put a tetrahedron on top of this octahedron, an octahedron on top of this tetrahedron. So this is a tetrahedron, I put an octahedron there, and this is a tetrahedron here, this is my another octahedron, this is my cubic close packed structure, and this is related to my hexagonal close packed structure by actually a twist, right, about the central atom. And the twist will occur along this axis. And how do I visualize the twist? If I try to twist all these atoms, all these voids, they will fall down. So let me do the twist with a single pair of voids. In other words, to go from a tetrahedra on top of an octahedra to an octahedra on top of a tetrahedra, of course I could do a translation like this, wherein for instance I take an octahedra on top of octahedra, but more precisely I can do this twist around this. So now what happens, I get a tetrahedra on top of a tetrahedra, an octahedron on top of an octahedra, and it did this rotation about this axis, for instance. Equivalently, of course, I could do another operation so that I can get an octahedra on top of an octahedra and a tetrahedron on top of a tetrahedron. So this can be done, and you can see these two structures are closely related as far as the voids goes. In terms of the coordination polyhedron, we had seen that it's a cube octahedron in the case of the cubic close packed crystals, and in the case of the hexagonal close packed crystal, it was a twinned cube octahedron, and we have coordination models which reflects this twinning operation. So we have a void model here, and let me summarize once again the salient features of this void model. That this model is very useful, especially in making calculation, as I said, number of voids per atom, right. So in other words, how many, suppose now I have certain atom, for instance a carbon atom sitting in the octahedral void, I would know that how many carbon atoms can sit around a central atom, for instance of iron, in the cubic close packed crystal. So those kind of calculations are very easy to make with this kind of a void model, and additionally it helps you visualize the voids, the way they can fill space. And I also pointed out that the same set of voids, the regular octahedron and the regular tetrahedron, can be used to make the cubic close packed crystal as well as the hexagonal close packed crystal. So there are these void models. I have here a model of the hexagonal close packed crystal, wherein I have 3 layers of atoms. The basal layer, there is 1 layer of atoms in the middle, which, as I had pointed out, goes part of the motif, and there is a 3rd layer above. And here I want to illustrate the presence of the octahedral and the tetrahedral voids. Let me start the easier of the two, which is the tetrahedral void, and as I pointed out, the tetrahedral void is made by 3 atoms in the basal plane and an atom which is sitting above. So let me lift this model up and show from a different camera angle the same thing. So here I got my tetrahedral void, which I want to show from a different direction. So this is my tetrahedral void. So there are 3 atoms in the basal plane and 1 atom in the C equal to half plane, which constitute my tetrahedral void. Now, where is the unit cell of this crystal? So I can consider my unit cell as this rhombic prism. This is my unit cell, and therefore this tetrahedral void, for instance, lies completely within the unit cell. But I can locate an alternate tetrahedral void whose orientation, as we saw, is opposite to that of this tetrahedral void, and that can be formed by this atom which has been painted red and blue, the one in the basal layer, and these 3 atoms which are in the C equal to half plane. So these are the 3 atoms, 1 red and 2 blue, and 1 which is painted half red and half blue. Putting together these 4, I would get a tetrahedral void which is pointing downwards. Equivalently, I could locate another tetrahedral void which is pointing upwards by taking this atom and these 3 atoms. That means I take this brown atom, this red atom, this blue atom, and this blue atom. So this will form the base, triangle base, and this will be my 4th, which will form the tetrahedron. As you know, tetrahedron is nothing but a triangular pyramid. So I have this tetrahedron right here. So I can have 2 tetrahedrons which have centers along this vertical edge, and since this vertical edge is no different from the other vertical edges like this and this, therefore they will also be seats of centers of tetrahedral voids. So right here along this edge I have one tetrahedron pointing upward and one pointing downward. Now this model is very illustrative to understand the position of the octahedral void. So now let me take an equivalent unit cell, for instance this unit cell formed by these 4 atoms, 1, 2, 3, 4. Similarly on the basal plane there is one brown colored atom, one blue colored atom here, another blue colored atom here, and an atom which is colored half blue half red. So these 4 along with these 4 corners here, vertices here, would form the rhombic prism, which is the unit cell for the hexagonal closed packed crystal, with this atom at C equal to half contained within the unit cell. Now the octahedral void is, as I pointed out, shared between more than one unit cell, in fact 3 unit cells. So now there is this unit cell which contains one atom which belongs to the octahedral void, there is this another unit cell which contains one more, and there will be an equivalent unit cell here which contains one more atom. In other words, this octahedral void which is shown here with its vertices colored blue, so there are 3 triangular atoms which form a triangle which are sitting in the basal plane, 3 in the mid plane, which are the 6 vertices of the octahedron, and out of this these 3 in the basal plane all sit are contained within, of course have at least some part of it within this unit cell, but there are these 2 which lie completely outside the unit cell. Therefore this makes a little difficult to visualize the octahedron with respect to the standard conventional unit cell. So let me go over this process again. So I got my tetrahedral void which can be contained completely within a unit cell. Of course I could also visualize other tetrahedral voids which lie between unit cells, and I have this octahedral void which is always shared between the conventional unit cells. So this is pointing this direction, of course, as you know, this is my seat of the 6-3 screw axis. In other words, this is the A position, this is my B position, and the C position is completely vacant, which is the seat of the 6-3 screw axis, and along the center, along that axis lies my octahedral void. And the octahedral void, as you can see, has these atoms as its vertices. And since these voids are actually the solid models of the voids are actually shrunk down versions of this actual polyhedron, and this has been done for just better visualization, you should remember the actual void would be formed by these faces which are right here, these full complete faces, but these are just shrunk down versions for better visualization of the centers of the voids. Okay. So I have this unit cell having part of this void, this alternate unit cell having some part of the void, and this a third unit cell having some part of the void. So these 3 unit cells together form the complete, put together those parts, I get the complete octahedral void which is located with its 3-fold axis upwards. So this model is a very illustrative model, and let me take a little time out to actually show this model from various perspectives. So this you can see, this is model in this perspective. You can go around this a little bit to actually visualize the voids. And let me rotate it around so that I can actually show you the C axis. Using this opportunity, let me show you an alternate model for the position of the voids and the kind of spheres which can sit in those voids. So let me show how, and we have seen a model like that before. For instance, now this is my set of spheres here, transparent glass balls which have been used to fill the unit cell in a cubic closed packed crystal. So I got these void models here, and let me take out central sphere and put a void. This is so I want to show the relative sizes of the atoms. So you can see that the size of the atom which can sit in the void is considerably smaller than the size of the atom which goes into the lattice. You can see that the relative sizes clearly. So let me put that in the central void position. As you know, this is my octahedral void position, and therefore I put an atom which goes and sits in the octahedral void. So that is my atom. To show an atom which actually sits in the tetrahedral void, I have got an alternate sphere here, and you can see that this atom is even smaller than the atom which goes into the octahedral void. So let me show the relative sizes. So this is my atom which goes into the octahedral void, which is a bigger void in the cubic closed packed crystal. this is my atom which goes into the tetrahedral void, which is smaller, and of course I have my sphere which is larger than both of those. And I know my seat of the tetrahedral void, and let me carefully try to put it here, to put an atom into the tetrahedral void. This is a slightly difficult task because the atom would tend to fall into the lower tetrahedral void or this sphere, so it does not matter. So let me try to get it into the, so this is my tetrahedral void where my atom can sit. Okay. So let me see. So anyhow, so the point I want to make here is to actually for you to get a feel of the relative sizes of the atoms. So let me maybe try to put it in this tetrahedral void, which may be slightly more successful if I can pull out this atom. Yeah, so this is my position of the tetrahedral void. So I manage that. So you can see that now I have an atom sitting in the tetrahedral void, which can be seen, which is a smaller atom, and there is an additional atom right at the center which is sitting in the octahedral void. So this is my center of the tetrahedral void, this is my center of the octahedral void, and you can clearly see that the relative sizes of these three spheres. And I got my space filling solid here. So you have to remember this when you are actually trying to make interstitial alloys, which we will study later, that since these spheres which can fit into these voids are rather small, the solubility of some of these are very limited. So let us once again use this transparent sphere models to understand the relative sizes of the atom which can sit in the octahedral and tetrahedral voids in the BCC crystal. So I have shown here two unit cells of the BCC crystal, wherein I have atoms like this which sit in the body centering positions, and these atoms sit on the vertices of the cube. Of course, I could grow this crystal further by putting more of these spheres along the vertical direction. So this would again be body centering positions. Now the size of the relative size of the two atoms which can sit in these vertices are shown here, and I would not take the risk of putting them into the spheres because they will tend to fall down into wrong places. So this is my largest sphere which can sit in the octahedral void, this is my largest sphere which can sit in the tetrahedral void. So let me place them down here for relative sizing. So I got my three sizes. So you can see that the size of the spheres which can fit into these octahedral and tetrahedral voids are rather small. So this is the this is, as we saw, 0.15, 0.29, and this is my full size sphere which is at the lattice point. Now let me try to locate the relative positions of these voids. The octahedral void, which is a smaller void, and as we saw that the atom sitting in the octahedral void only touches the atoms which are above and below it. So the center of the octahedral void is right between these two body centering positions, which is right here, or equivalently between this body centering atom and an atom which I place above. So right between these two kind of atoms is my octahedral void position, wherein this kind of a sphere would sit. Now the tetrahedral void is, as we saw, located between, if you take a midplane like this, it is located, if you take a half midplane, then it is located at the center of that half midplane. So in other words, my tetrahedron which is formed between 1, 2, 3, 4. This is my vertices of the tetrahedron, and as we saw, this is not a regular tetrahedron, this is a distorted or a non-regular tetrahedron. So let me locate my octahedra. So let me take, say for instance, this sphere. So octahedron is made of this central sphere 1, 2, 3, 4, 5, and this is my sixth. So this is my octahedron which is made by 6 atoms, and my tetrahedron is made by 1, 2. So 1 in this body centering position, 1 in this body centering position, and this 3, 4. So this is my tetrahedral void. So and relative sizes, as we saw before, are these which can sit in these relative positions. So let us look at the voids in a BCC crystal, and as we had pointed out, there are no regular shaped voids. In other words, the voids which are present in the BCC crystal are not one of the 5 platonic solids. As we shall see, you can call them distorted, or I would prefer the word is non-regular octahedral and non-regular tetrahedral voids which are present in the BCC crystal. And we shall see that I would rather use the word non-regular rather than irregular, because, or distorted, because we shall see there is some symmetry to these non-regular tetrahedron and the octahedron as well. An important point to be noted, and we will actually try to make some calculation based on this concept, is the fact that the distorted or the non-regular octahedral void is actually not even an octahedral void. In other words, an atom sitting in the of the right size sitting in this octahedral void actually will be touching only 2 atoms, and this is an important point to be noted. And a very surprising thing which is coming out of this analysis is the fact that in BCC iron, carbon prefers to sit in the smaller octahedral void, and we will try to understand the reasons of this based on the configurations around the voids. So, where are the voids in the BCC crystal? So, there are 2 kinds of voids as we saw. The one on the right is the non-regular octahedral, one on the left is the non-regular tetrahedral void. So, let me consider first the tetrahedral void. The tetrahedral void is made up of the edges are 2 different kind of lengths. The tetrahedron consists of this and this 2 lengths which have a length A, which is nothing but the edge length of the unit cell. Additionally, it has got these 4 which are marked in green, and the length of this edge is root 3 A by 2. In other words, it is half the body diagonal of the cube. So, even though it is a non-regular tetrahedron, it has not been fully distorted, and as you can see, you can have a 2-fold direction which is going along the centers of these edges. Now, the 3-fold directions have been lost because of the distortion. Now, where is this center of this tetrahedral void with respect to the unit cell, and let me locate it, for instance, using this cube. So, the tetrahedral void, suppose I have my face like this, I take half my face, okay. So, this is my half my face which is a rectangle, it is located in the centroid of that rectangle. So, I have a model here to show you where the tetrahedral void is located. So, let me show you this wireframe model. So, I have these 2 unit cells right here. So, I can divide this unit cell into 2 halves along the mid plane like this, and now if I take the central face which is shared between these 2 cubic unit cells, then I would note that it is at the center of that half rectangle which is made of this face. And as I pointed out, this tetrahedron is made up of 2 lengths, one length which is red, which is shown here, which is A, and this blue length is root 3 A by 2, and this is my 2-fold axis of this tetrahedron. So, how many of these tetrahedron would come at each face? As you know, this cubic unit cell has a 4-fold axis which goes along the 0, 0, 1 direction, and that means if this is one tetrahedron void, there will be 4 of them in each face. And how many unit cells will this tetrahedron be shared between? It will be 2 unit cells, because half of that would lie within this unit cell, half of that would lie in the unit cell above, as it has been shown in this figure that each one of these tetrahedral voids is shared between 2 unit cells. So, each of these faces again would have similar kind of configuration of 4 tetrahedral voids which are shared between 2 unit cells. Now I need to locate the octahedral void, and as I pointed out before, this is a non-regular octahedral void, and even though as I pointed out before these voids are called octahedral, they actually have only 6 atoms at their vertices. So, the octahedral void is located at the face centers. So, when I draw 2 unit cells and this is my octahedral void, the center of the octahedral void is at the face center. Now, again this octahedron made of 2 edge lengths, the length which is marked in brown is A, and the length which is marked in green is root 3 A by 2, exactly the 2 kinds of length which were involved in the tetrahedral void. Now, if I try to put an atom at the center, then this length from the center of the void to the atom which is being colored orange, noting again that the orange color is just to distinguish the position, and all atoms are identical in this BCC crystal. Now, this distance is A by 2, while on the other hand this distance is from here, from this vertex to the center, is root 2 A by 2. This is A by 2 and that is root 2 A by 2. In other words, if I put an atom of correct size fitting within this octahedron, then it will be only touching the atoms which are up and above and below this void. In other words, it will not be touching the 4 in the mid plane. In other words, this octahedral void actually turns out to be a linear void. If the atom we are putting in is of exactly that size which can fit into this void without causing distortion. Now, what is the relative size of these voids with respect to the host atom sitting in the lattice position? For the tetrahedral void, the ratio of the void size to the atom radius size is 0.29. For the octahedral void, it is about approximately half that, which is R void by R atom is 0.155. As you can see, these numbers are smaller than the void size numbers which we had noted for the cubic closed pack crystal. So, what are the numbers we had noted for the cubic closed pack crystal? We saw that the tetrahedral void was 0.225 and the octahedral void is 0.414. So, we can see that especially this octahedral void is considerably smaller than any of the previous voids we have encountered. And if this position is a seat of the octahedral void, then I can add any of the body centering translations to land up with other equivalent positions for the octahedral void. For instance, I could add to half of 0 to this position, which is 0 0 half, and I will land up with all BCC translations to land up with equivalent identical points, or sorry, this is to be half of half, which is a body centering translation. Now, let me locate the so in other words, I will land up with an octahedral void position which is at the center of an edge, which is 0 0 half. So, that means if I have an octahedral void located at half of 0, then the center of the edge, which is related by a body centering translation to this position, is also a center of a non-regular octahedral void. So, I have octahedral voids in one which looks at the center of the unit cell and all which look at the edges. So, with the important point to note, this octahedral void is actually shared between 2 unit cells, as you can see above and below, while this octahedral void is shared between 4 unit cells, this one, the one above, one to the left and one below that. So, I have shown only the octahedral and tetrahedral voids located within on a single face of the unit cell, but we have to remember there all the other symmetry translations, symmetry operations of the cube, or the 4 by m 3 bar 2 by m symmetry operations will give me all the equivalent positions of the octahedral and tetrahedral voids. So, we have the distorted tetrahedral void, we got 4 by 2, which is the one which is one located within we saw here, this kind of a thing, and there are 6 of these faces. So, I have 12 of these tetrahedral voids per cell. As far as I am talking about the octahedral voids, they are located in the face center and they have a contribution of half. So, there is 6 faces, half contribution there are 3, and there is one at the edge center which is located here, and its contribution to the unit cell is 4. I have 12 edges, so 12 by 4 is 3. So, I have 3 plus 3, totally 6 voids per cell. So, I have 6 octahedral voids per unit cell in an BCC crystal. I have 12 tetrahedral voids per cell in the BCC crystal, and as there are 2 atoms in every unit cell of the BCC crystal, I can divide this 12 by 2 to get 6 voids per atom in the BCC crystal and 6 tetrahedral voids per atom, and there are 3 octahedral voids per atom in the BCC crystal. Now, having seen the relative sizes of these voids, the smaller being the octahedral and the larger being the tetrahedral void, I would like to again just confirm this by a calculation that actually this is the size of the tetrahedral void. So, let me do a calculation that where is my tetrahedral void located? It is located at the centroid of the rectangle, which is made by half this common face. So, if I look at the tetrahedron here and I look at the central of the tetrahedron position C, then I can draw a right angle triangle CMO or OCM, and the length OC can be got by Pythagoras theorem to be root 5 by 4a, which is nothing but, so the OC is where the atom sitting in the tetrahedral void will be touching the atom sitting in the lattice position. So, that will be equal to R plus X. For the BCC structure, I know that the atoms touch along the body diagonal, therefore, root 3a is equal to 4R, in other words, a is equal to 4R by root 3. I can substitute this value for R. So, R plus X becomes root 5 by 4, 4R by root 3, which is R plus X from this equation. Therefore, X by R is root of 5 by 3 minus 1, which is 0.29. So, using simple geometry, I can actually calculate the size of the atom with respect to the size of the atom sitting in the parent lattice, which can fit into this tetrahedral void. So, similarly, I can make of course a calculation for the octahedral void, and noting in this case that my atom is now be touching along the OB direction. So, my atom along the OB direction, which is a by 2, which is nothing but 0.5a, and that is equal to OB is equal to R plus X, because now the X atom, which is my foreign atom, or the atom sitting in the interstitial position, would be touching the atom sitting in the parent lattice, and that is equal to A by 2. And so therefore R plus X equal to 4R into 2 root 3. Now this is OA. For instance, this OA is my root 2A by 2, and I know for BCC crystal root 3A equal to 4R. Therefore I can calculate my X by R to be 2 root 3 by 3 minus 1, which is 0.1547. Now again, this is of course very simple kind of geometry which I am applying here to understand my kind of species which can sit in the tetrahedral and octahedral voids, and a student is just requested to go through these calculations once again to convince himself to that these calculations are right, and also to understand the relative configuration of the atoms when they sit in the octahedral and tetrahedral voids. Now as I pointed out, we will consider the special example of carbon in iron and the relative size of the atoms, and especially when you are talking of a carbon sitting in BCC iron with respect to a carbon sitting in FCC iron, to understand how the solubility, for instance, would be affected by these relative size of the voids, and which void the carbon atom preferentially sits in. So in the case of the FCC, it is very clear that the larger void is the octahedral void, and when I add carbon to gamma ion, which is the FCC ion, the carbon would sit there, and there is no confusion regarding that. But in the case of the carbon in BCC ion, as I said, it surprisingly carbon sits in the smaller octahedral void, which I pointed out in some sense is actually a linear void, and we will try to understand why this is so. Now however, we notice that with respect to both the voids which are present in BCC, even the largest of the voids are smaller in BCC. This is somewhat surprising, because we know that the BCC is an open structure, but we already seen the number of voids in BCC is more than that in FCC. In other words, BCC has more number of smaller voids. Even though there is larger amount of space available in BCC crystal, it is divided up into smaller sized voids, and that is why my carbon actually finds it difficult to sit in any one of these voids which are actually small, and this would affect its solubility. And we know that carbon actually, the solubility at room temperature and alpha ion is extremely small, it is of the order of 0.001% or something very small, and the gamma ion, which is found at higher temperature, actually has a much higher solubility for carbon. So to repeat this important point, we know that BCC is an open structure. So for at first glance we would assume that actually we will have a higher solubility of carbon in BCC ion. But when carbon tries to sit in the BCC voids, the distortion cost is more and the solubility of carbon in iron is smaller. This is because the number of voids in BCC, or the total space available in voids, is actually split up into smaller size, larger number of voids, and this is why my solubility of carbon in BCC ion is smaller. Of course, this is one of the reasons. There are other reasons which would come up from various other aspects which we need to consider in detail, but this is sort of an first level understanding of the solubility of carbon in iron. So let us look at the relative sizes of the voids, and especially with respect to the size of the iron atom. The first thing I would point out in this transparency is the size of the iron atom itself. For instance, the size of the iron atom in the cubic closed packed crystal is 1.292. This is of course an approximate value which is different from the size of an iron in the BCC crystal. So this is something to be noted. That means that the size you calculate is also dependent on the crystal structure. Now of course, what is the size of an atom, how do we calculate it, is a subject by itself, and typically I would assume a spherical distribution of electron probability and use some value to truncate to get some value of the radius of the atom. But I need to note this important point, that the radius is not equal in these two crystal structures, and I have drawn a sphere here to indicate the size of the iron sphere which sits in the FCC crystal and also that which sits in the BCC crystal, of course which are approximately similar. Now let me locate the size of the carbon atom, and the size of the carbon atom happens to be 0.77 angstroms, which is drawn here to relative scale with respect to the green iron shown atom. Now size of the octahedral void in FCC crystal is also shown here for relative size, and as you can see, the carbon atom is bigger than the octahedral void size. Now, so this is my octahedral void side, which happens to be 0.534 angstroms, while the carbon atom is 0.77 angstroms. Therefore, the void is smaller than the size of the carbon atom. So, even though, as I pointed out, the solubility of carbon in iron, gamma iron is more, which is the FCC form or the cubic close pack form of iron, even then we note that the void is not even enough to fit a carbon atom. The void just happens to be good enough to fit, for instance, an hydrogen atom, which has a diameter of about 0.46 angstrom. So, that can fit into an octahedral void, but if you take any other atom like a nitrogen, which is itself a small atom, or our carbon, which is of technological importance, this would not comfortably fit. That, in other words, when I try to put carbon into FCC iron, there will be solubility, but then this solubility is limited by the kind of distortion it causes to the lattice. Of course, initially we consider only dilute concentrations of carbon in gamma iron. When we take up the BCC crystal, then we see that the void sizes are considerably smaller. This is now my octahedral void, which is smaller, and the tetrahedral void, which is bigger, is also smaller than the octahedral void or any of the atoms. So, my void of my tetrahedral void in BCC is about 0.364. So, which means that even an hydrogen atom cannot fit into this void. So, it will cause distortions when it tries to fit into this void. Well, definitely the octahedral void is even smaller, and its diameter will be 0.195 angstrom. So, its radius is this, and therefore, its radius is 0.195 angstroms, and therefore, it is smaller than the tetrahedral void and considerably smaller than the carbon atom. Now, let us try to answer this question which he had raised, that why is that the carbon goes and sits in the octahedral void, and the answer turns out that when I try to put a sphere, which is now my carbon atom, into this, it has two options now, the tetrahedral void, which is a larger one, or the octahedral void, which is a smaller one. So, it can choose one of the two, and I pointed out that it actually goes and sits in the smaller of the two. The reason is that when it sits in the octahedral void, and it is definitely bigger than the octahedral void, but still it needs to only push 2 atoms out of place when it sits in the octahedral void. While if it sits in the tetrahedral void, it is actually touching all the 4 atoms, and as the carbon atom is bigger than the tetrahedral void, it will be actually pushing 4 atoms outward. So, the distortion it causes to the lattice, and hence the energy it causes to the system, is larger if the carbon atom tries to sit in the tetrahedral void, while if it is in the octahedral void, it can only push out 2 atoms and try to make space for itself. So, of course, I will try to make an ideal calculation to see till what size will it end up only pushing 2 atoms. So, this is of course an ideal geometrical calculation, which is highly simplified. When you try to push 2 atoms outward, that will lead to a chain of other distortions which will end up actually squeezing this octahedral void shape, but I am ignoring all that just to show that there is considerable space available if you are willing to tolerate pushing only 2 atoms. So, as before, I consider now my octahedral void in the BCC structure, and I choose my 110 plane to illustrate the point I want to make. The 110 plane I have chosen because along the 110 plane, which is shaded green here, I can draw my 111 direction, which starts from this point A and goes to the opposite body diagonal here, and the atoms in the BCC crystal touch along those direction. So, my atom which is sitting in the vertex here, I have the atom which is sitting in the body centering position, and the atom which is sitting in the opposite vertex. So, again I have overlaid all the atoms here on this 111 plane, and this being my 111 direction, and this direction now is my 110 direction, which is nothing, the 110 direction, the connecting A vector to the opposite vertex here. Therefore, I have my 111 plane here, and sorry 110 kind of plane here with 11. So, the actual plane would be 11 bar 0, and I have my 110 vector lying on this plane. So, if an atom which is now compared to the size would be 0.15, the atomic size, the fraction would be here, then it would be touching only these 2 atoms, will not be touching the remaining 4, which is 1, 2 are shown in this plane, the remaining 2 would be on this vertex and that vertex, and they have not been shown in this diagram. So, they will be touching only the 2 atoms which are colored orange here. Now, assuming the ideality, it can expand till it reaches a diameter which is shown in dotted line without having to push these two atoms. So, this is sort of an ideal geometrical calculation. Once again, I need to emphasize that you can continue to put larger and larger spheres into this small hole here, which is shown here in the middle, without actually having to push these two blue atoms. So, this is what I was trying to say, and this is the reason that the carbon actually wants to sit in this smaller octahedral hole. But again, I need to point out that these are simplified first level understanding, and a deeper understanding would come from a more detailed calculation, wherein you actually try to fit atoms of this and make an ab initio calculation of how that will affect the energy of the system. So, now let me try to calculate what is the size from O to X, and ignoring, of course, for that I will ignore the atom sitting in B, and assuming the interstitial atom touches till the atom touches at A. So, this is what I will try to make a calculation. So, now my OA is R plus XA. So, this is my atom at X, which is now the expanded atom, is equal to root 2A by 2, and R plus XA is equal to 2 root 6 by 3 R. Now, writing in terms of R, which is for the BCC crystal. So, I can calculate XA by R to be 0.6329. Okay. Now, trying to translate this into real dimension, my OX will be that is for the BCC iron crystal is 0.796 angstroms, while I know my carbon atom, so this is 0.796 atom. So, let me compare it with the size of the carbon atom, which is of the size of 0.77 angstroms. So, this OX is larger than the size of my carbon atom, and if you compare this with OY, which is a smaller number, is 0.195. So, I can see that if a larger size sphere is put into the BCC crystal, it would rather go and sit in the octahedral void and push out two atoms, which would cost my system lower energy, and it will continue to do so till it start touching these atoms which are sitting in A kind of position, which have been shaded blue. And this explains two things, of course, why the carbon atom goes and sits in the octahedral void, but additionally it also points out why the solubility of carbon is extremely small in BCC iron. So, to summarize, this explains this X by R ratios between 0.15 and 0.63, and again pointing out these are some sort of a simplified calculation. The interstitial atom has to only push two atoms, and therefore, it would go and sit in the octahedral void. So, with this we have made a sort of an overview of all the voids which are present in the cubic closed pack crystal, the body centered cubic crystal, and the hexagonal closed pack crystal. And we saw that for the CCP and the HCP crystal, the voids are identical, and they are the regular tetrahedron and the regular octahedron. The BCC crystal has larger space of void, but is divided into smaller voids which are large in number, and this is an important point to be noted. And this aspect also would later on determine some of the other aspects like diffusivity, etc.